Joint work with Richard Merrows about asymptotics of the hyperbolic metrics under nodal degeneration. Then I'll talk about its application to Weil-Petersson metric. First of all, let me introduce the main object to study. So we take a compact surface of genus G. Here we require genus to be greater than 2. And over the surface, there are some complex structures. The moduli space is the space of complex structures on the surface up to diffeomorphism. And because we are on dimension 2, real dimension 2, complex structure and metric structure there is a bijection between each other. And also, we also interested in the moduli space of MGN, which is genus G surface with n marked, ordered, distinct points on it. And so let me draw a picture. So this is our moduli space, MG. I should also say, in the MGN case, we're interested also in the stable range, which is 2G minus 2 plus n greater than 0. So when n is 0, this is why we are in G greater than or equal to 2 case. So this is our moduli space MG. Each point is a complex structure on the surface of genus G. There's a space called universal curve, which fibers over this MG, which is basically just this tautological bundle that over each point, I have my surface with this given complex structure by this point. So at each point, there is a complex curve. So this universal curve space is identical to MG1, the genus G surface with 1 marked point. So this is easily seen from the picture here. As we move along the curve here, this is just given out the marked point on the genus G curve. And the projection, the fibration over MG is just given by forgetting the marked points. So this is universal curve fibered over the moduli space. By uniformization theorem, we know that on each curve, there is a hyperbolic metric with finite area. And also by uniformization theorem, we know that this hyperbolic metric varies smoothly over the curve. This can be seen by looking at the curvature equation because the uniformization theorem gives us existence, and using ellipticity, we can show that this metric varies smoothly. So as Tektajan mentioned yesterday, on the moduli space, there is a metric called Weil-Petersson metric, which is defined using the hyperbolic metric on the fiber. This is the main object to study for this talk. So as we know, the moduli space is not compact. And there are, Derlin Mumford gave out this compactification of the space by doing an algebraic geometry method. So this corresponding to adding nodal divisors. So nodal divisors are basically the most simple singularities we can add in for this kind of curve. So this is we add some divisors into MG to compactify it. And also we compactify CG, which is just MG1. So after the compactification, MG1, bar MG1 over MG, bar MG is a singular fibration. So the two main questions to ask here is, since we are adding some exceptional divisors onto this moduli space, how does the Weil-Petersson metric behave when we approach the singular divisors? And because this moduli, the Weil-Petersson metric is defined using this hyperbolic metric, and so we want to ask the second question is, how does the canonical hyperbolic metric vary when we approach the singular fibers? Okay. So first of all, let me talk about the degeneration of singular fibers. So over the singular divisors, the nodal points are added in. This corresponding to this pinching geodesic behavior. So this is taking a surface of genus G. Here in the picture, I used genus equal to 2 case. And we take a geodesic circle on the curve. Then we let the geodesic to shrink until it shrinks into a point. So in this process, it introduces a pair of nodal points. This is called geodesic pinching, and this is the behavior of the nodal crossing. So the previous picture might be misleading because eventually this picture needs to be in the nodal crossing. There are two disks that are transversally crossing to each other instead of the picture that we see it's a pinching. So in the one-dimensional complex picture, it's really just a curve that crosses each other. And locally, this behavior looks like this. So in the crossing here, if we enlarge it, this locally is modeled by the following behavior called Plummet variety. So a Plummet variety is the following vibration, singular vibration. We have ZW inside C2, and over this vibration, it maps to T, which is a product of ZW. So if we zoom in around the neck here, this is what we see. We have a neck. So here, this is T equal to 1, and there's a geodesic circle here. When T becomes smaller, this neck becomes thinner. And finally, when T equal to 0, this becomes two disks transversing to each other. And this is given by Z equal to 0 and W equal to 0. So this is the Plummet variety. So this, by introducing this nodal crossing model, we show that, well, we know that the boundary, which is not boundary because it's a divisor in the complex geometry, but we say that the quote-unquote boundary is a union of normally intersecting and self-intersecting divisors. And for each singular behavior, it corresponds to pinching one geodesic, and that gives a pair of nodal points. And if, say, we have a higher genus curve and we're pinching several geodesics, this it will introduce, say, if we pinch k geodesics, this will introduce k pairs of nodal points. And this will lie on the intersection of k local divisors, where the k local divisors are all parts of this mg minus 1, 2, which is G minus 1 genus, and we have a pair of nodal points. Also, I should say here, this degeneration doesn't change the arithmetic genus, because this arithmetic genus is 2G plus n. So say if we go from mg to mg minus 1, 2, this is still 2G. All right. Now, after introducing the divisor, we want to talk about the Weil-Petersson metric. So the cotangent bundle of the moduli space is naturally identified with the holomorphic quadratic differentials on the fiber of mg1, which I'm going to talk more about it later. And more importantly, this Weil-Petersson metric, metric defined on the cotangent space is given by the following push-forward formula, which is we take two holomorphic quadratic differentials, we take the inner product, then we divide it by the area form of the fiber hyperbolic metric. Then we do the integration over the fiber. This will give us a metric. So as we see, the two main important elements in this Weil-Petersson metric definition is the holomorphic quadratic differential and hyperbolic metric, which is why we want to study the degeneration of a hyperbolic metric on this nodal degeneration. So Weil-Petersson metric, this subject has been studied by a lot of people. This slide is by no means a complete coverage of all the papers. but I'd like to mention several of them. So for hyperbolic metrics undergoing this nodal degeneration, Weil-Petersson, Wolf, and Albizzo all have done some work. Especially, we're going to use the methods of Albizzo and Weil-Petersson in 2009 to deduce the asymptotics of the complete asymptotics of this hyperbolic metric. Then the geometry of moduli space is, first of all, it's Burrs that introduced a set of coordinates on the moduli space. Then Deligne and Mumford, as I said before, they used algebraic geometry to show that there is a compactification. And Robin and Salomon used their universal unfolding to talk about the cotangent tangent space of moduli space, which we're going to use for the compactified case. And for Weil-Petersson metric, the asymptotics across the divisor, I'd like to mention Mathieu and Swoboda deduced this metric, the behavior of the asymptotic on MG this year using a somewhat different method. And I'm going to focus on MG, the unpointed case, in my talk. And later in the next talk, Richard will talk more about the pointed case. And there are a lot of problems that are related to this Weil-Petersson metric behavior, especially Takhtajan and Zograf and Albizzo. They showed some property about this Takhtajan-Zograf metric, which is closely related to this Weil-Petersson metric, which will also be talked about in the next talk. Okay, so after talking about this whole literature review, let me go to the first topic, which is the hyperbolic metric. So we improved. Let's now focus on the case where a curve that degenerates into a singular curve. So we want to know like what the behavior of the hyperbolic metric is. So here is a previous results by Albizzo and Weil-Petersson. What they show is they use a metric called Plummy metric, which I'm going to talk about later. And they show this the constant scalar curvature metric has this conformal factor with this Plummy metric, and they computed the conformal factor up to the third term. So one thing to notice here is there is this parameter log tj, which is identical to the length of the geodesic, which is also the one we are going to use. So what we are going to do is we basically follow their construction of Plummy metric, and we show that there is a complete asymptotic expansion of this metric. So what we do is we show that there exists a resolution of the total space, M hat. I'm going to talk more about it. And under this resolution, we show that the metric is conformal to a log-scaled Hermitian metric on the tangent bundle of the new space, where the conformal factor is log smooth. So first thing we want to do is we want to find a space such that the metric can be smooth, or at least log smooth on it. So how we do it is we first focus on the local model. Okay, let me do it. So for the local model, we focus on the Plummy variety there, which is a degeneration of this hyperbolic cylinder into two normal crossing disks. There is a Plummy metric living on this, which is a fiber metric over the space, which is given by the following. For each t, it's given by this expression, which is pi log z over log mod t over sine of pi log z over log t squared times G naught, where G naught is this metric dz over z log mod z square. Okay. So there are several things I want to say about this fiber metric. First of all, it's a fiber metric. So for each t, it defines a metric over the fiber zw equal to t. First thing to notice is that when t goes to 0, this quantity goes to 1. This is because log mod z over log mod t goes to 0, and by this classical limit x over sine x, this quantity, the conformal factor here, goes to 1. Therefore, when t goes to 0, this metric, fiber metric, approaches this g naught, which is the standard form of Cusp metric over this transversal disk. The second thing to notice is that this metric, after change of variable between z equal to t over w, this whole metric, this whole expression here wouldn't change. Wouldn't change is all the z becomes w. Therefore, this expression is symmetric with respect to z and w. And the third thing is the most important thing is this, the Plummet metric actually provided an exact hyperbolic metric on this Plummet variety. For each given t, this metric has constant scalar curvature -1. So this is the model metric we want to consider. And the first thing we want to do is we want to find a space such that this family of metrics can live smoothly over there. As we can see, there are some singularities here. There are log and there are quotients. So this is the first thing we want to do. So this starts our resolution of the space. So first of all, the space, the model is there, this hyperbolic cylinder degeneration model here. As we see, when t goes to 0, there is this angular variable. So there's like a rotation variable here, which is singular. So the first thing we do is we introduce this angular variable, which in geometry corresponds to blowing up the central divisor. So this is our first step, is we introduce angular variables. And in this case, just the real effect is all the coordinates becomes real. So this is the same as saying we introduce the following space with z and w, with mod z and mod w as coordinates. And then there are two circle fibrations nearby, not nearby, as a product. And the plumbing vibration, zw equal to t, this time becomes a real vibration, meaning all the nearby fibers becomes mod z mod w equal to mod t. So in geometry, it looks like this. The second thing we want to do is, because there are a lot of log here, and the logs are not smooth in the space here. So second step is very natural that we introduce more boundary defining functions, meaning the log boundary defining functions. So the picture will basically look the same, except the boundary defining functions this time will become I log z and I log w. Here, I log z is defined to be 1 over log 1 over mod z. So this function basically is the same as introducing log mod z as a smooth function. Also, when mod z goes to 0, this I log z goes to 0. Therefore, it's an effective boundary defining function. So the vibration still looks like this. And also, this is not only introducing log on the vibration, it also introduces log into the base. We also introduce this I log t, which is the same definition. That's 1 over log 1 over mod t. Okay.
When you say
yeah.
introduce these functions, does that mean any polynomial in these functions, or does it mean any function of these functions for the I log?
Any
how much are you expanding the function?
Any smooth functions.
Any smooth function of these functions.
Okay, yeah, so this is actually why we need to do step 3. So for step 3, once we do this change of variable, this plumbing metric after all the change of variable becomes the following, where it's a fiber variable, it's a fiber metric on the totals on the fiber. However, it still includes this I log t there. And as we see, because t equals to z times w, so if we do the following computation, that's I log t is the following 1 over log 1 over t, and we introduce t equal to mod z times mod w here, and expand it out using I log z and I log w. This is the following expression, that's I log z times I log w over I log z plus I log w. And this expression, if we divide it by I log w, this becomes I log z over 1 I log z over I log w plus 1. So this is a function over this plane spanned by I log z and I log w. However, this is not a smooth function over this plane here, because we have this quotient here. The ratio of x over y is not smooth over the plane xy. So because there's approach in this corner here, it's not smooth. You have different directions, which is why we want to introduce the third step of resolution is we want to resolve this corner here. Oops. So the final picture will look like this. Still, the boundary is I log. And we introduce a new phase here, which is the same as introducing this ratio of two functions as a new smooth function in the space. Okay. And and I should call this new phase called phase 2, and this original phase, which is the punctured Riemann surface, as phase 1. Oops. So this is the final resolution we want to have. Is we do the 3 steps of resolution, we get the space. In the 2-dimensional picture, it looks like this. So for all the regular fibers nearby, it's still this hyperbolic cylinder. It doesn't change because we don't do anything on the fibers. But for the inside central fiber, what we do is we introduce this new cylinder inside, which is phase 2. This is a 2-dimensional picture. And also we introduce this log as boundary defining functions. Therefore, there are more smooth functions living on this space. So this is the smallest possible space that plumbing metric can be smooth, as we just see. And I call this space when it's connected with the outside Riemann surface M hat. So this is a resolved space over the original M, and over the base, the T manifold as Z, then this is M hat over Z hat is a new vibration. Okay, so after doing this resolution, what we get is there's a B vibration of the new thing, which meaning that the boundary defining function on the base lifted up to be a product of boundary defining functions over the total space. And also, the more important thing is this fiber tangent bundle over this M hat after log with scaling, meaning that we use this log as boundary defining functions, is the bundle that possibly this metric lives in. And what we do next is we take a smooth Hermitian metric on the fiber on this fiber bundle. Then we solve this curvature equation to find the conformal factors. The main result about this hyperbolic metric is we deduce that this fiber metric, the hyperbolic metric, behaves as the following. So it's a continuous Hermitian metric on this log rescaled tangent fiber bundle, and is related by with a smooth one by a conformal factor, which is essentially smooth. However, it can include log terms, which is log of the boundary defining function. So in original variables, it's like log t. So this is the main result. What we do is we solve this curvature equation. So let me show how we do this. Let me erase this. So first of all, let me write down the curvature, the scalar curvature change under a conformal transformation. So if a new metric G equals to a conformal transformation of the original metric G naught, then the scalar curvature changes under the following equation, which is the first line of equation. So this is also the same as the classical Liouville action as mentioned yesterday by Tecta Zhang. In our case, what we want to do is we want to take this G naught to be the Plummy metric, meaning it's locally near this Plummy variety, it's this Plummy metric. However, we also use this grafting technique used by Abitsu and Woppert to get a total metric, or a total fiber metric, which is Hermitian on the new resolved tangent bundle. Then we call this the Plummy metric. And after this, and we substitute the thing we want. That means we want this the scalar curvature of the new metric to be -1. This the second equation is we will want to solve. So that's Laplacian of the Plummy with respect to the Plummy metric plus the scalar curvature of the Plummy metric equals to -e to the 2f. So one thing to note here is by using this grafting technique, the scalar curvature of this Plummy metric has the following property. So this Plummy metric is basically -1. However, there's an error term which has the following decay that's given by I log t to square. Okay. So let me draw the picture again. This is 2 and this is 1. So basically, the scalar curvature of this original Plummy metric is good here. It's -1 here, and it's -1 outside. However, there's an error term living here, which is compactly supported, and has the following decay when we approach this boundary here. So once we get this in there, once we substitute this condition into the equation there, this is what we get. This is Laplacian. Well, it's written there. And this is a nonlinear equation about the conformal factor f. So what we do is we do the linearization. So this is, once we expand this e to the 2f as in the linearization, this is what we get. Laplacian of Plummy metric plus 2 applied to the conformal factor is -1 minus r, the scalar curvature of the Plummy metric, which is of the following order. So this is eventually the linearized equation we want to solve. And as we see, this Laplacian plus 2 operator comes out, which also appears yesterday. And we want to solve this conformal factor with a error term that's log t square every term. So as I said, we want to solve this linearized equation. And what we do is we do the following. So we do this because we have this circle vibration. We can do the Fourier transform. We can do this. Take the Fourier series. So for non-zero modes, the solution decays exponentially, so we don't need to worry about that. But for the zero mode, this becomes, when we restrict to the zero mode, this Laplacian plus 2, this linearized operator becomes an ODE on each face. And we analyze the behavior of this ordinary differential operator.
But I log T is a bounded defining function of phase 2, is that right? Or
it's a bounded defining function with 1 and 2. This is
one
T here.
one.
Yeah. T is Z and W.
Yeah, okay.
So what we do is we compute the inducer roots of this ordinary differential operator on phase 1 and 2. The following is so we obtain two inducer roots for two phases. For phase 1, it's 1 and -2. And for phase 2, this is inverse 2 and -1. Then what we do is we solve this ODE iteratively by first solving it on phase 1. Then once we solve it, there's an error term that's propagating to phase 2. We solve it on phase 2. Then we propagate back to 1. Then do this iteration between 1 and 2. So one thing I want to mention here is this appearance of extra log terms. So this can be seen by the following very simplified model. So the appearance of extra log terms usually occur when the two inducer roots are differed by an integer. And here, suppose, say, for example, if we have an operator rho d rho, and the inducer roots of this operator is 0, because we just substituted this into this equation, we will find alpha equal to 0. However, if the forcing term if this rho to the alpha appears in the forcing term, i.e. we have this rho d rho, we want to solve an equation with constant c, then here you would become c times log rho. This is just by solving simplified ODE. So this is one way to say that why we suspect there will be log terms, and because when we solve this equation on this phase 1, there will be forcing terms appearing on phase 2. Then it will hit the inducer roots. Then we will get log terms. And once we have log terms, the log terms will just keep propagating. Then it will just keep growing. And also, okay, let me say that in the next one. And also, we show that this linearized operator is invertible on suitable weighted Sobolev spaces on this resolved space, which is going to be used later for invertible result for perturbation argument. Okay. So by the process I just described, by this iteration between phase 1 and phase 2, what we get is we get an asymptotic expansion of this conformal factor f here. So f is expanded using this I log t as a then there's a I log t, and there's a coefficient before I log t, and k starts from 2. And because of the process I described earlier about this appearance of extra log, so in general, this coefficient fk would have extra log terms in terms of t.
Just log terms? I mean, just powers of log or anything?
Oh, just powers of log. Yes. So in general, it will look like something like t to alpha, then log t to the I log t to the beta. And also, we show that this growth of the logarithmic terms can only be linear, meaning that alpha cannot be bigger than alpha in this case. So after that, after this asymptotic expansion, we use this invertibility result of the Laplacian plus 2 to show that there is a genuine solution nearby for the true curvature equation. So by this, we show that the existence of the conformal factor on this grafted surface, and which gives this hyperbolic metric in the case. So what I just described is just we just decreasing one geodesic circle to 0, but as I described earlier, in the moduli space, if the genus of a space of a surface is higher, then there will be several geodesics shrinking. So this is used. Then we use this model, the following model, to show that a similar result can be obtained about this linearized operator and the curvature equation. So this is done by using this multi-Lefschetz fibration, meaning basically there are multiple z and w projected to t, to different t's. This is by using this projection phi. And we use the following picture to show this process. So in the picture, this blue, I think it's blue. In this picture, the blue curve is a regular curve, it's a smooth curve with no singularities. And the purple curve is we decrease one of the circle into a pair of nodes. So that's and the yellow curve is we decrease the other one into a pair of nodes. And this black one in the center is the central fiber where both GD6 are decreased to 0. So this picture is an illustration of what happens when several ones got shrunk to 0. And what we do is we do a similar process, similar iteration process as to the 1 geodesic case. That is, we blow up at every nodes, meaning we introduce, if there are k pairs of nodes, then we introduce k different phase 2. Phase 1 is the original one because that's the one with cusps. So what we do is we do the iteration, except this time we start with curves with cusps. And as this cusp metric, this hyperbolic metric with cusps is known already, then we start from this hyperbolic metric. We start to solve this Laplacian plus 2, the linearized equation, except this time the error term would have the following decay that's it's compactly supported, and near each surface it has this decay of I log t1 and I log t2 and I log tn to square. Then we solve this equation iteratively along each phase. Eventually what we get is this conformal factor is basically the same, has this polyhomogeneous expansion, and the log terms, this time there are several different variables. The log terms will appear in linear growth in terms of this, in terms of the polynomial. So after using this, we showed that the hyperbolic metric under this nodal degeneration can be characterized using the conformal factor. Okay, so this is the whole process of solving this hyperbolic metric degeneration problem. Now, using this, we want to characterize the Weil-Petersson metric on moduli space. So as we know, the cotangent space of the moduli space is identified in a regular point, meaning in a point with no degeneration, is identified with holomorphic quadratic differentials. And when on a divisor, it contains, on a divisor meaning on a pair of nodes, it contains meromorphic quadratic differentials with poles at most degree 2. So what we want to do is we want to identify it with a geometry which is a log cotangent bundle. We want to say that the quadratic differential, this cotangent space, actually lives in a bundle called log cotangent bundle. So this let me talk a little bit about the log geometry. Okay. Let me erase this part. So as we approach, as one approaches the divisor, there are two directions. The first one is this across the divisor action direction, which is given by complex number t. And then along the divisor, there are some other variables, z. So z is just not only a variable; it's just it's a set of variables. Then there's this log tangent bundle, which contains all the vector fields that are tangent to all the divisors. So locally, it follows this tangent bundle. Locally, it's spanned by dt over t dt. And other dz. This is a log tangent bundle. And then by duality, there's this log cotangent bundle, which is locally spanned by dt over t and dz. So what we say here is this logarithmic cotangent bundle, which is locally spanned by those forms, would be the cotangent vectors that the moduli space actually lives in. So we extend the proof of Robin and Solomon to show that there is a natural isomorphism between this kind of log cotangent space and log cotangent bundle and the bundle of holomorphic quadratic differentials on the divisor. So intuitively, I like to give a dimension counting argument here. It's not an argument; it's just an intuition. So as we know, the complex dimension of a moduli space on MGN is 3g minus 3 plus n. Then if we degenerate into a divisor which is nearby mg minus 1 and plus 2, then the dimension, if we just put in this g minus 1 and n plus 2, it's 3g minus 1 minus 3 plus m plus 2. And if you compute that, we'll find there's an extra 1 missing. So this 1 actually comes from the residual of this log cotangent on the nodes. That is how the cotangent bundle matches with the cotangent bundle on the divisor. And this is and the proof of we use extending the Robin and Solomon is basically consider the solvability of D-bar operator, which eventually is another form of Riemann-Roch. Okay. So after we introduce all the resolution, which meaning we do this resolution, the 3-step resolution I described earlier, then we can find this resolve space mg1 hat over mg hat. And then under this vibration, and use a push-forward theorem under the bundle here, we can show that the Weil-Petersson metric is log smooth over the log cotangent bundle I just described earlier, using the hyperbolic metric, the expansion of hyperbolic metric. So that's how we show that the Weil-Petersson metric is log smooth. Okay, I'll stop here. Thank you.
Are there any questions?
in this iterative process that you use to solve your PDE, is it clear that, I mean, how do you show that it ends, that it converges?
How do you show that it converges?
Yeah, I mean, you do like one near phase 1, then near phase 2, then you get something near phase 1, then go back, and then you need to control errors.
Yeah, the coefficients here are basically smooth, except it has log terms, linearly growing log terms, and
It's a Browns function.
it's Browns
That's
theorem.
implied.
Yeah.
So you say you have that the growth of the log terms is linear. Do you know what the constant is in the linear growth of the log terms? Like in the depends on n, I suppose, the crossing.
It depends on n. So in the one dimensional, in the one case, the constant is 2. Yeah, but for more degenerating, it's computable. Yeah.
Not just like 2 to the n, but
It's probably 2 times n. Yeah.
Okay, anything else? Thanks, Xuwen, again.